Hello everyone. This morning I came across an interesting tweet where someone named Sean has posted a menu for chicken wings. The chicken wings have a very kind of unusual pricing structure where the restaurant is laid out prices. Apparently, Math Twitter has gotten a hold of this and looked for a closed form solution that's I don't know if someone's found one or not. But as a computer scientist, I take one look at this and I see that you can apply dynamic programming to solve this, where let's say you wanted to buy 33 chicken wings. Well, you can't buy just 3. You could buy 30, but you can't buy 3. So you're going to have to find some other configuration, like let's say 28 and 5. But is 28 and 5 the optimal price? I don't know, but we'll find out. And in fact, apparently some other people have noticed some other interesting values where I can't spot an example just off my head, but let's say the 50 is not actually the optimal price. Maybe if you buy 2 sets of 25, it would actually be cheaper than 1 set of 50. We can use the dynamic programming approach to solve this. So in case you're not familiar with it, dynamic programming is a discipline of algorithms that was pioneered by Richard Bellman. The name is super misleading, and I own this book and I don't understand it, so yeah. So let's just dive into the code, and I'll show you what I've got. Let me take this away. In fact, before we look at the code, let's look at the data. So here's the before. So we have all the same data that's shown in the tweet. Notice that many values are empty, right? There's no price per wing for 31 because 31 is not an option, so we don't yet know what the total cost would be or what the configuration would be. And so what we're interested in is we want to minimize the price per wing. And if we have the price per wing, then we just multiply the count and the price per wing to get the cost. If the price per wing is minimized, then the cost is also obviously minimized. And we'll want to know what the configuration is. What is the optimal configuration? So the way this algorithm is going to work, we're going to start at the 4. We assume that we can't do any better than the 4. So we will actually, starting at 4, we're going to see, what if we add 4 and 4? If we add 4 wings to 4 wings, we're going to get some cost. Is that less than 8? And it looks like it is not. It's actually exactly the same. So we're not going to overwrite that. And now we're going to move on to the 5. So we'll add 4 to the 5, and we'll see, is 4 and 5, does that beat the 9? And I think that it does not. Now we'll add the 4 and the 6, and we'll see, can that price beat the 10? And if it does, then we'll overwrite that. And what we'll do, if it overwrites it, is we'll say that we want a 4 and a 6 here, and we'll fix the costs and price per wing. And we're going to do this, starting at the 4, we're going to add 4 to everything, all the way down. And so an obvious one is if we add the 4 and the 30, we're going to initialize this value to be something like what it'll mean to us to be infinitely large, and any price is going to beat infinity, so we're going to end up with a 4 and a 30 here. But then later we might find that a 5 and 29 is actually a better cost. So once we've gone through every value and with adding the 4, we're going to move on and now add a 5 to every value in the table, and then the 6 and the 7. So that's a lot of operations. It's a quadratic number of operations that we're going to do, but it will give us an answer. Professor Demain at MIT refers to this as careful brute force. This is not a brute force algorithm, I think. This is dynamic programming. We're going to find an optimal solution, and we're going to find it with a lot of iterations. So now on to the code. So here we've got all the data. I just typed this in. These are 2-dimensional arrays where every one of them has the number of wings and the total price for the wings. And I'm going to have 2 tables. One of them is the price per wing, and the other one is the configuration. And we'll initialize those data structures by going through all of the elements in data. We'll say that our configuration initially is just the string version of the number of wings, and the price per wing at that position is going to be equal to the price divided by the number of wings. Now we move on to our dynamic programming algorithm where we iterate, starting at the 4, moving all the way to the limit. Limit in this case is 201 because Python's treating this as not inclusive, so we want to include the 200. Starting at the 4, we're going to go through every number of wings, and if we haven't exceeded 200, then we're going to take a look. We're going to look at the total, at the price per wing by multiplying I, and this we're starting at the 4 times the price per wing of that, plus j, that's the other wing that configuration we're looking at, times its price per wing, divided by the 2. So that gives us our new price per wing at that I plus j. And if that beats whatever's already in the table, which we initialize that as a value of 100,000, which just effectively means infinity in our case. If it beats it, then we override it, and we save what that configuration is. Once we're finished through these 2 loops, we come here and we loop through each one, and we print what those optimal configurations are. Let's run the code. We see that it runs very quickly on this is a relatively old laptop. And here the values are. Let's take a friendlier look in Excel. Here's the optimal configuration, count, price per wing, cost, and configuration. We see that at number 17, we beat whatever the wing menu price was. So let's take a closer look at that. It says it's 7 and 10. So we're saying that 19.3 is what the menu had, but at 7 the price is 7.95 plus the 10 is 11.35. Can we do this in Excel? Equals. Not actually in Excel group. Oh, this may be a rounding error in Python. This may be that it was. Yeah, that's a shame. It is interesting that we found one that's equal. We can go on, and so now I don't really trust my data as much as I did before. But I hope that this is useful. So we see that, like, if we wanted to buy 79 wings, the optimal configuration for that is 28. I didn't realize that we went up to that many denominations. Okay, I guess we did. 28 and 51. Oh, 51 is a strange option because 51 I didn't think was an option. So I guess it's 28, 25, and 26, which is a real shame because I have to go back to this. Uh-oh. Well, anyways, so probably, man, super disappointing. 625 and 65. Super interesting. Well, anyways, so that's the idea. Yeah, wasn't really expecting it to look like this. So, man, I have to look into it a little more, I suppose. I think I know what I've done wrong. This should not have been string j. This should have been config j. So we'll just do, yeah, not config I. Well, I guess it would have been that. Config I and config j. And I think I'm just going to publish this to the tubes anyways, just as is. Let's run it again. And there we go. Now we got something new. I've never posted text. So now this is probably more interesting, right? You know, now we have hopefully the same numbers, but oops, oh man, I was trying to undo in the other tab and it didn't let me. Hopefully the same numbers, but we see that there's kind of strange topologies in here. We see that the 200, according to this algorithm, 25, 25, 25, and 125 wings is the optimal configuration for this. So there you go, dynamic programming for the win. I'll post this code somewhere.